Good afternoon, everyone. So let's wait for 5 more minutes. Let's see if anybody joins, then we'll start. Okay, so we'll start. Mm, if you do not join on time, you can still follow the lectures on YouTube channel, which link has been shared by the NPTEL team. So this is NOC EE-62 NPTEL tutorial of basic electronics. Just to make sure you are on the right course. The instructor is Professor Mahesh Patil from IIT Bombay. I am a TA to the course. I am Debashish Nandi from IIT Kanpur. As you know that we go live every Sunday 3 to 5. Let's proceed. So as a prerequisite, as I have already iterated it several times, again I'll iterate it that you must at least have gone through the previous week lectures, right? Which were posted in the course web page. And also you're expected to attempt the assignments at least once by yourself so that it is useful for you to go through this tutorial session. Also, whoever has joined, please keep your microphones muted all the time. You can raise hand, you can use the raise hand option. So if you have any query, or you can just put it into the chat box, right? I will give you time to ask your query after every topic I covered or every problem I solve. Then at the end of this 2 hour session, you will be given a 10 minutes time to ask your general query regarding the session, right? And please keep a scientific calculator with you. This will be very helpful to follow the session, right? So this is week 4 and we'll start. So let me just zoom into it. So the question is asking about consider a half wave rectifier with peak voltage of 25 volts, this frequency of 50 gigahertz, 50 hertz, and a filter capacitance of 500 microfarad. Okay, so the ripple voltage is to be limited to 2 volt. What is the lower limit of the load resistance? Okay, let us first dwell into the topic, right? Let me know if the screen, the font size is is not visible or you need some update, right? So the topic here is half wave rectifier with capacity filter. Let's first discuss about half wave rectifier. Suppose just hold on a minute. If this is VI, how will my VO look like? Let's say VI is Vm sine omega t, right? Let's say this is your input voltage and it goes on. So this is your VI, this is your Vm. So how will your this output voltage look like when, let us assume that the diode is ideal. So when you have the positive half cycle, the diode will be on because the potential drop across it will be more than its cutoff voltage, which is for ideal diode is 0 volt. So for the positive half cycle, the diode will be on and we will get the output voltage as same as input voltage, right? And for the negative cycle, there will be no conduction because the diode will be in reverse biased and it will be an open circuit. and the similar phenomena will go on, right? So this is how a half wave, this is your V out, right? Now the question is the purpose of rectifier circuits are that we want to convert the AC signal to DC signal, right? And we want to use that DC signal as a supply voltage to some DC power supply to some electronic circuits. Now see if this VM, let's say as in the question, is 25 volt, so you have a ripple output, right? So how can you overcome to this? One way is that if I can make my output stay at this voltage, right? Then I can have a constant DC voltage which I can use in my circuits. So how can you modify the circuit to have a constant DC voltage? So the idea is that half wave rectifier circuit with a capacitance across its load. Let's say, let's first draw the circuit diagram. So this is your input voltage, Vm sine omega t, or it may be cos omega t. It's just a phase shift, right? And you have a capacitance here, you have an ideal diode, and this is your output voltage, V out, right? So how will this look like? Again, if you draw your signals, let's say this is your input signal. For the positive half cycle, the diode will be charging and diode will be on and the capacitor will get charged, and capacitor will get charged when V naught is maximally equal to Vi, and what is that? That is Vm. So when V out is equal to Vm, then the capacitor is fully charged, right? Now see the input is reducing from this point, this time stamp onwards. Let's see, it is omega t, and it is pi by 2. From pi by 2 onwards, the voltage across the input voltage is decreasing from Vm, right? It has to be toggling between Vm plus Vm and minus Vm. So the voltage across capacitor will remain my Vm, and the diode will get cut off because, let's say, if this node is V, this point is Vi and this is Vo, at say just this time instant, let's say t omega t1, at omega t1 your Vi is less than Vm and your V naught is Vm. Why V naught is Vm? Because this is cut off and then the capacitor cannot discharge. It has no path to get discharged, right? So the capacitor will store its voltage, and the net potential across diode, your Vd, is now less than Vd is now less than 0, right? Vd is now less than 0. That means Vi minus V naught is less than 0. So it will not conduct. And till what point it will not conduct? It will not conduct until unless my Vi is more than Vm, right? Then only the diode gets forward biased and it will start conducting. But you see that my sinusoidal signal is never going to cross this Vm. So what about my output? My output will just stay here. At this point again, the net voltage across my diode is 0. So it keeps on going on, keeps on like that, right? So here you can see, if we see the, if here you can see, if we just focus on the steady state part, right? We can see that we have a constant DC voltage. That is the main purpose behind this capacitor across this half wave rectifier, right? So now the point is, this circuit we have discussed in the last tutorial. Can you just pause the video and tell, if as no participants has joined, so I'll request if you can pause the video and remember what is this circuit, right? So yes, you have guessed it correctly. The circuit is a peak detector circuit because it is detecting the peak of the signal, right? And this kind of circuits are used in amplitude modulation, amplitude modulated signals, demodulation of AM signals. Let me put it in this way: demodulation of amplitude modulated signal. This you will read in your analog communication course, what is amplitude modulation and how you demodulate it. This is the simple concept. Just let me, for the interest, this is, suppose this is your message signal, and say, suppose it is your message signal, and say it is your carrier signal, right? You generally have your carrier signal at high frequency. Say it is your carrier signal. So in amplitude modulation, how, what is your modulated signal will look like? Your modulated it will signal will look like something like this. This is the envelope of the signal, and the signal will be off at carrier frequency, right? So this is the signal your receiver will receive. Your receiver will receive this kind of signal, but you need to find out this, right, this envelope, because this is where the message information or the message is stored. So how do you do that? You just simply plug this signal to a peak detector. Just plug this to a peak detector and it will just detect your this peak, the envelope of the signal. It will just demodulate and provide you the message signal, right? So this is one application of the peak detector circuits. See, we should always know why we are reading the subjects, right? And what is the application. We should never lose focus on from that point. That any theory is fine, but we need to understand the application. So let me, a more practical, a more practical, let's say, half wave rectifier plus filter circuit. Filter circuit. Okay. So how will you go about this? Ideally, you will not have only a capacitance, a capacitor, but you will also have a resistance across it, right? So you need to analyze this circuit. This is your VIT and this is your V out, right? In this case, how will my waveform look like? Let's say this is your input signal, and let's say this is your output, right? So when it is getting charged for the first time, it reaches the peak value Vm, and after that what happens? After that, the capacitor here is heavy. This if this path is cut off, let's say if this path is cut off somehow after reaching this maximum, we know for an ideal if there is no resistance, then this will the diode will be reverse biased and capacitor will store the voltage, right? Now what will happen if there is a path for the capacitor to discharge? So after this the capacitor will start to discharge, right? It will start to discharge exponentially. Capacitor discharge exponentially, and your output will output voltage will eventually fall, right? So suppose till this point the capacitor is discharged, and at this point what happens? Your Vi is also rising, right? As soon as your Vi is rising, this diode circuit will get activated, it will get on, and then it will again start charging the capacitor. Do you see in the charging path there is no resistance, right? So the capacitor will immediately start to follow the input voltage. So it will again start to follow the input voltage, and again when the peak is reached, it will start to discharge. Okay, so your waveform in practical sense will look like this. So now let me show you. Now you will realize what is the issue here. Let's say this is my sinusoidal signal, and suppose you are getting charged, and then this is your output voltage. So instead of a constant voltage, what we are getting? We are getting a ripple, right? We are getting waveform like this. This is called ripple. So what is happening in this case? You will have this is your Vm, right? And this is the lower limit of your ripple voltage. So let's see, this peak to peak ripple voltage is Vr. This is your V. This is your V out. This is your Vm, and this value is Vm minus Vr, right? So we have to make sure that this ripple voltage is very small compared to the peak voltage of the input signal, right? So how can we achieve that? We can achieve that, as we know that this is you can see this is an exponential decay, right? So you want the circuit to behave like this, ideally, right? And what will this decay depend on? This decay will depend on my time constant, RC, right? If my RC is much large, ideally if my RC is infinite, that means this R is not present, which is the earlier case for an peak detector circuit, right? For an ideal peak detector circuit. There we have no resistance. A parallel resistance not present means R is your infinite. So if your time constant is infinite, then what happens? Then this becomes a straight line. But in ideal case, there will be some resistance. So if you can ensure this condition, your RC is much greater than the this time period, right? And what is this peak to peak? This is nothing but your period of the signal, right? So you can reduce your ripple voltage limit. So this is a very important condition. Now we want to develop the mathematical tool to analyze this circuit, right? So let me again draw this circuit. This is your R, this is C, this is your diode, and this is your input, this is your output. Okay, say Vi is Vm cos omega t, let's say. So how about your ripple voltage, right? This voltage. Let me again draw the same waveform. This is your input voltage because it is already rectified. Then this will be your output voltage. You can see if you can ensure this condition, right? RC is much greater than your time period. Then the discharge time of the diode, the discharge time of the capacitance is almost equal to your time period. Okay, so we'll consider this as the discharge time of the capacitance is equal to the time period, and this is your Vm. So, and this value is your Vr. So now what will be this value? This Vm minus Vr. This value will be your Vm exponential minus T by Rc. How did I write this equation? When your diode is off, right, your circuit will become nothing but this. Some initial stored voltage will get discharged across this. It will be nothing but the natural response of an RC circuit, right? And your initial voltage stored at the capacitance is maximum voltage, that is your Vp, that is your Vm here, that is a peak voltage. So this will be your Vm minus Vr will be your Vm exponential minus T by Rc. We know that T is much less than Rc, so exponential minus T by Rc can be approximated as 1 minus T by Rc. So your Vm minus Vr equals to Vm 1 minus T by Rc. So your Vm, this Vr is becoming Vm into T by Rc. Okay, we'll remember this formula. So now let us go back to the question. So they are asking, consider a half wave rectifier with this Vm is given 25, F is given 50 Hertz, C is given. We need to find out the R value. Okay, simply from here we can solve the problem. Just let me solve it here. Your Vr is Vm into T by RC. We need to find out R, which will be Vm by Vr into 1 by T is your frequency into C. That means 25. Your ripple voltage is said to be 2 volt and your frequency is 50 hertz and capacitance is 500 microfarad, right? So 10 minus 6. So if you solve this, your answer is coming up to be 500 ohm. This is your answer. So is there any option? Yeah. So 500 ohm is the C is your right option, right? So let's move on to the next problem. Okay, no option is given. Here they are asking that for this condition given in the Q1, what is the average diode current, right? Now let me see how can we find out the diode current. This is your diode, this was a resistance, a capacitance, this is your VI, this is your VO, right? So we need to find out the average diode current. So the if you see if you see this is your diode current, right? This is your IR, say this is IC. That means your ID is nothing but IR plus I of C. So I can write that IR is not going to change because it is the voltage will remain at certain value and your R is constant, right? So VD average or diode average current is nothing but R plus IC average. Now we need to find out how to go about this IC average, right? So finding out IC average, we can simply equate the charges that your IC average into your delta T. Let me tell you what is delta T here. Delta T is this time duration, right? This time duration. So this into delta T will be equal to your C into VR. This is your net charge stored by the capacitance, right? During that delta T time. And during that delta T time, it will be similar to C. What is the voltage difference here? This is nothing but your VR, right? So we need to find out IC average. IC average is nothing but, and your IR here is Vm by R. Let's remember this current. When the peak value is there, right? The peak value of the output voltage is Vm. So we need to find out C into VR by delta T. Now another bottleneck has arrived. How do we find out this fellow, right? How do we find out delta T? You see from this diagram, this delta T can be delta T can be found out by Pm cos omega delta T is nothing but your Vm minus Vr, right? From this equation, we'll be finding out our delta T. So your Vm cos omega delta T is equal to your Vm minus Vr. Okay, and again your delta T will be very small if your RC is much greater than T. Then you can simply delta T omega you can simply write as 1 minus delta T omega whole square by 2. And if you don't understand this, then I think you are aware of this thing. We can write the cosine as an infinite series like this. So I am taking just this first two terms because if x is small, these terms will be very small, so I can neglect that, right? So if you solve this, you will find Vm 1 minus delta T into omega whole square by 2 equals to Vm minus Vr. Then this is your Vm gets cancelled. Then omega delta T becomes 2Vr by Vm square root. Okay. So from here we can substitute to find out IC average. Your IC average is nothing but C into VR by delta T. By delta T, that means your root over 2VR by Vm into 1 by omega. That means C into VR into root over Vm by 2VR into omega. Now we know the expression for VR. Let us substitute VR here. VR, we know Vm into T over RC. Vm into T over RC into omega into root over Vm by 2VR. This we can write as 2 pi. This we can write as IL. Sorry. This we can write as I. What is the notation I have been using? IR, right? This we can write IR. So CC cancel. So it becomes your pi into IR into your 2 pi, 2 will be coming inside. So 2 Vm by VR. Okay. So we find out that IC average is this. So ID average we can write simply as IC average plus IR. That is, if I take IR common, so it is 1 plus pi root over 2 Vm by VR. This is the expression. ID average is equal to IR 1 plus pi root over 2 Vm by VR. Okay. Here, remember the assumptions that we are assuming. We are assuming here that RC is much greater than T. Delta T is very small, right? So ID average in our question, IR we can find out simply by Vm by R. So Vm is 25. R, what is the value of R? We found out to be 500 ohms. So 500 ohms into 1 plus pi root over 2 into 25 over, this is 5, not 5. What is your VR? Your VR is 2 volt, right? So this cancel. So it becomes 1 by 20, 1 plus, this is 5 pi. And if we calculate it, 5 shift pi plus 1 divided by 20, it becomes 0.835 ampere. Okay, this is your answer. And you find out that in the similar manner, your ID max should be nothing but twice this, right? 0.8 ampere, it will be around 1.6 ampere. Actual exact expression, if you find out, and how do you find out that exact expression of ID max? Oh, next question is this only. The peak diode current ID max is nothing but 1.6. There was no option for 2, right? So how do you find out? I just let me tell you the steps. ID max or peak diode current, that would be your, you know that ID is nothing but your IR plus IC, right? And how do you can write your IC? IR plus C dV dt, right? From this equation, you can find out your ID max. You just need to consider this is your input voltage, this is your output voltage. So let me just, you take this as 0 and this was your delta T, right? The conduction cycle, remember that this is your delta T here. So you just solve it for T equals to minus delta T, because at this instant your current will be maximum. Let me show you. This is your voltage, this is omega T. How will the current waveforms look like? Your current waveforms will look like, just let me, so if you see your current waveforms, I will look like nothing but, at this instance your diode is off, so ID will be 0. At this instant ID will be maximum, and again at this instant your, this will be 0, right? Similarly, again from this instance your, this will be 0. And just let me, for the sake of clarity, just do this, because your ripples will be like this only, right? So this is your ID waveform. ID will be just like this. Okay, so you can see at the instant when my diode starts conducting, my ID is maximum, and then when it reaches the peak, at that point my diode is getting cut off, or diode is moving on to reverse bias, and as I have considered it as a ideal diode, so diode current will be 0, right? And you can easily see the waveform of your this also, this will be similar to your voltage waveform. Okay, this will be like this. Okay, this is nothing but your IR. Okay, your IR waveform will be like this. Now see some interesting notes here. You see the ID average is equal to IR 1 plus pi root over 2 Vp by PR, right? This was the expression we found. This was the expression. So you see, generally your Vp is much less than VR. That means this term is much more than 1. That means your ID average in general is much more than your load current, right? Or the resistor current. And this is also quite evident because you see that this is the time when this is the duration when you have the discharge time, right? The capacitance gets discharged and the charge flows. During that time, you have some current. But to replenish that charge, how will you, how much time you have? You have just this instant. You have just this window, right? So obviously your average diode current which flows during this window will be much higher than your this current, right? Your IR, which is considered to be constant in this case. Okay, so moving on to the next problem. That is, what is the maximum reverse voltage across the diode? My diode is an ideal diode, right? So let me again draw the circuit. This is a capacitance. This is a resistance. This is my V in, which is Bm cos omega t per se. This is C, this is R. So my input voltage is like this. What about my output voltage? Output voltage is like this, right? So also let me just tell you what is the voltage if I just consider this rectifier, right? Should always remember this point also. Okay, this is without RC filter. This is your output output with RC filter, and this is your input, right? So let's say for what is the reverse voltage, right? So this is your V out, this is your V in. So your reverse voltage is V out minus V in, right? V reverse across the diode. When it will be maximum? Let's see. This has to be maximum. This has to be minimum for this to be maximum, right? What is the V naught maximum? V naught maximum is this point, V max, right? So V naught maximum is Vm. at that instant, do we have the value of this? Where did it go? Do you have the value of Vi? Your Vi is also same, right? Vi is also at that point Vm. So your Vr is nothing but 0. But what about this point? At this point, what is your V out? Your V out can be fairly approximated to Vm, right? Because capacitor is storing holding the charge. So let's tell it T1, it's T2. This we discussed at T1. So V0 max, let's say not V0 max, let's say V0 at T2 is equal to Vm, and Vi is nothing but minus Vm, right? What about your Vr then? Your Vr is V0 minus Vi is 2Vm, right? So can you see that Vi minimum, and this is also my Vi minimum. So Vr maximum cannot be more than this value, because at this instant my V out is maximum and my V input is minimum, right? So this 2Vm is your maximum attainable reverse bias voltage across the diode. So what was my Vm? My Vm was 25 volt, right? So your Vr max should be nothing but equal to 2Vm, and that is 50 volt, and your C is the right option, right? So this way you can analyze any diode circuits. Okay. So far we have discussed diode circuits. Last week we have discussed on some, uh, I think some sort of clippers, clampers, and that Zener diode circuits, and some peak detector circuits also. This week we have discussed mainly the peak detector circuit, and first of all we discussed how an ideal half-wave rectifier will look like, and then we discussed that how a peak detector circuit will be behaving if there is no resistance present for the capacitor to discharge. Then it will store the DC value, and this is the desired, because we have a constant DC voltage which I can feed to the next electronic supply, next electronic equipment and feed this signal as a constant DC supply, right? Which is desired. DC means we need a constant voltage. So we have seen the usage here, that it can be used in demodulation of amplitude modulated signal. Then we have gone to the more practical one, where there will be some resistance and the capacitor will be discharging. That means my time constant is not infinity. That means the peak voltage will get reduced and the capacitor will get discharged. So in that case, I will have certain amount of ripples, which is more practical, but we do not want that. So how can we tackle that? We can tackle that as RC if the time constant can be made much more than your discharge period or the time period of the input signal, right? So then we analyzed what will be the ripple voltage condition on my frequency. It depend. We can see that it depends on my VR. VR depends on my VM. Obviously, frequency of the signal. This is time period is nothing but 1 by frequency and my RC time constant, right? So as you can see easily from here, if your RC is infinity, VR is 0 simply, or you can see if RC by T ratio determines your, the more this will be, my VR will be that much lesser, more desirable, right? So next on we have encountered certain numerical examples. One was to find out this ripple voltage. We can simply use this formula, but we should always remember the assumptions that my RC is much more than T. That's how I can curtail this Taylor's series to just first two terms, right? Then we have found out the average diode current, what is the value, and this is also delta T. We have found out what is delta T. Delta T is nothing but the diode conduction time. If this is asked, this you can also find out easily. And then we have found out the average current across capacitor and eventually found out the average current across the diode. So we have also seen that how to find out the maximum diode current. We have seen the how does the diode current and the resistance current look like throughout the cycle, right? And then we have found out the peak reverse bias voltage, right? What that can be available at the diode end. See, remember that we have considering here ideal diode, right? If it is not ideal diode, and say I use the constant voltage drop model, which I discussed in the last to last lecture, right? Then that case I need to consider that zero point 0.7 volt cutoff voltage, right? That I need to take into account. I think that you can do, and this is for half wave rectifier. Similarly, these concepts can be used in full wave rectifier circuits also. A minor change will be there, and also some bridge rectifier circuits, which is eventually full wave rectifier circuits, right? So with this, we conclude our discussion on diode circuits. Next, we move on to BJT circuits. Okay, if you have any question, you can put it onto the chat. Let us take a 3-minute break. Okay. You can ask your question in the chat, or you can unmute yourself and ask your question. I see 3 people has joined. So if you have any question, you can ask, or let's take a break for 3 minutes. We'll join sharp at 4 o'clock. Okay, let's continue. There was a correction. This should be T2, right? This should be T2. I by mistake has put it to T1. This is this point. Okay. So let's begin with the BJT circuits. So let us first read the instruction here. So what they have told us that assume that NP and BJTs have VBE, base emitter junction voltage, is 0.7 volt in active and saturation modes, and VCE sat is 0.2 volt in the saturation region. Similarly for PNP junction, just a reverse thing, right? At room temperature. Also, thermal voltage is to be taken as 26 millivolt, right? Your thermal voltage VT is nothing but KT by Q, right? So you can convert it to any voltage of your liking. K is nothing but Boltzmann constant. It is nothing but 1.38 into 10 raised to minus 23 joule per Kelvin. I think you all are aware of this. T is temperature in absolute scale. Absolute means Kelvin scale. And your Q is nothing but your electronic charge 1.602 into 10 raised to minus 19 coulomb. Okay. And if you find out that T is equal to, find out for T equal to 300 K, which is 27 degrees Celsius, which is considered to be room temperature, then your VT turns out to be 26 millivolt. Not exactly, it is 25.9 more precisely. We'll take it 26 millivolt. Okay. So the first question is BJT operating in the active mode. Active mode. Okay. First let me tell you what are the modes. So operating regions of BJT, right? Region, emitter, base junction. This is collector base junction. So there are basically four type of modes for BJT operation, right? One we call this active or forward active. Here your emitter base junction is kept at forward bias and your collector base junction is reverse biased. And I am not going into that physics because for that it will be completely, there is a completely different course on devices, and you can just assume it like this way. It is a PN junction. It is nothing but a, let's say it is a PNP. So there are basically two junctions, right? These junctions and these junctions. So you need your carrier to go from this direction to this direction. You need your carrier to go from, majority carrier to go from this direction to this direction, which is, for that you need to put a positive voltage here, right? And you keep the base region width small, and you collect this holes out of this terminal, right? So you keep this as reverse biased. That means this, right? What happens if you keep it forward biased? If you keep it forward biased, then holes will try to move from this place to this place, which will really opposes the hole movement from here to here, right? And this will effectively reduce your hole transport. So this part we called as emitter, this part we called as base, this part we called as collector. This is nothing but a historical perspective. Why do we call these things? Because see, when the transistor was first invented by Shockley, let's say they had these contacts on a piece of substrate, and this was using as the base of the entire thing, right? I can show you the pictures, but I think I do not have it present right now. You can just Google it, any that earlier point contact transistor or any junction transistor, right? So these were emitter, these were collector, and for this holding purpose, this was termed as base, right? So that's how this name came from. So this is the forward active operation. Next is, and here the usage is in amplifiers. In amplifiers, we generally use this forward active operation, right? Then we have saturation. In saturation, what do you have? This has to be forward bias, and this also has to be forward bias. Then in cutoff, you need to have both in reverse bias. So what combination do we have we left? We left that this remains reverse bias and this remains forward bias. That is called reverse active mode. Generally, we do not talk about this mode, but it presents, right? Just so you know that it exists. So these are the modes of operation. These two are basically used in switching cases. You know, transistor can be used as switch, and as also it can be used as amplifier also, right? So these are the regimes where we, this you can say the off regime, this you can say the on regime, right? For the switching operation. Now let me tell you how this characteristics look like. EBE, this is IB. So see, this is nothing but a PN junction, right? And VBE is nothing but this voltage. Okay. So I am just this is for a NPN transistor. Let me say NPN. So this will be your forward bias. PN junction. How the PN junction forward bias characteristics look like? It is nothing but an exponential behavior, right? So this same trend will follow here also. And what about this? This is called your, see this side is called your input side, right? And this side is your output side. So if you want to draw the output characteristics will be looking like you have this. Okay, this is nothing but your IE is moving up. So if I have to tell you the regimes, so this will be your saturation, this will be your cutoff, this will be your saturation, this will be your cutoff, and this region is called generally forward active. What about reverse active? Reverse active, if you see, if you just keep the VCE negative in this case, you will find this kind of plot. So this, okay, so this region is basically your reverse active. Okay, so this is how we designate the range of operations. So okay, I think we can start solving the problems. So first question is that, let me copy the question. Okay, so they're asking us that consider a BJT operating in the active mode. Let us take this as forward active, because this is all, this generally this thing we do not use, right? So this is also called active also. Only active, if you see anywhere it is mentioned only active, just cross check with the bias condition, it will find out that it is a forward active region only. At room temperature, so your VT is nothing but 26 millivolt. Let IC is equal to this for some value of VBE. By increasing this to by this, we want to increase IC to 4 milliampere. What value of VBE is required? Okay, so just let me tell you that exponential VBE by VT. You can find the similarity here, that I am ignoring one term, a small value of that is called some VICO, that I am ignoring because this is much smaller. So you can write your equation. It is just similar to the diode equation, right? We know the diode equation, that ID is nothing but IS e to the power VD by VT eta VT minus 1, right? So this generally in forward active mode, it is much higher, right? It is exponentially increasing. So this you have the expression. So let's say your IC1 is your IS exponential VBE1 by VT, and your IC2 right. So if you can just take the ratio, this gets cancelled, it becomes exponential VBE1 minus VBE2 by VT. So if I turn this as delta VBE, that means my delta VBE becomes nothing but VT natural logarithm of IC1 by IC2, right? So let's say your, also it can be like it is your IC1 is, okay, no, not needed. So suppose in the question it is given that IC2 is equal to 4 milliampere and IC1 is equal to 2.5 milliampere, right? So your delta VBE2 minus VBE1, change that, we have just flipped the sign, okay? So your delta VBE would be nothing but VT ln IC2 by IC1, 26 into ln 4 by 2.5 millivolt. What does it come out to be? 4.4 divide 2.5 natural log of that into 25, sorry, 26, right? 26 into 2.5. It comes out to be 12.22 millivolt, right? So your correct answer is your B, right? A simple problem. Similarly, next problem, consider an, just let me zoom it out. Consider an NPN BJT operating in active mode. Again, this is forward active, room temperature, VT is equal to 26 millivolt. If VV is reduced by 0.02 volt, what is the percentage reduction of the collector current? Similarly, we know that IC2 by IC1 is nothing but exponential VBE2 minus VBE1 by VT, right? So your VBE is reduced by 0.02 volt. So your IC2 by IC1 is equal to exponential minus 0.02 by your VT is 0.026, 26 millivolt, right? So 0.02 divided by 0.026, exponential answer. So your IC1 by IC2 is becoming 2.15, right? So what is the percentage increase? Percentage decrease, rather I say. Percentage reduction, because the VB has reduced, right? Percentage decrease is nothing but your IC1 minus IC2 divided by IC1 into 100%. That is nothing but 1.15 by 2.15 into 100%, which is coming out to be 53.48%, right? So yeah, your A answer is correct. Okay, this is quite simple. Okay, so next problem is that in the circuit given below, assume that the BJT with beta is equal to 120. What is beta? Beta is nothing but IC by IB. Okay, and what is alpha? Alpha is nothing but IC by IE equals to alpha. Okay, and your IE is equal to IC plus IB. That means your beta IB plus IB. Generally, your beta is much more than 1. Basically, beta plus 1 into IB. You can assume it to be IC also. So that means your generally alpha is almost equal to 1, but it is somewhat generally less than 1. Okay. So this is beta called current gain. So operating in the active region, again, this is forward active. What is the value of RB? That will result a collector current of 0.8 milliampere, right? We need to find out the value of this voltage. Okay. So let me tell you how to solve these problems very easily. This is 0.68 kilo ohm, 680 kilo ohm. You can write 0.68 kilo ohm. This is your RB. This is 2 volt. This is 12 volt. This is your RC, right? So this is a loop. This voltage, this is a junction, PN junction. So this is nothing but your NPN. This has to be, this is NPN. How do you remember the direction of the diode? See, it is nothing but a PN junction diode. You can remember it this way, right? In a diode symbol, you know that PN, you can symbolize it as this. So for an NPN transistor, how do you just this how does this symbol come from? This I have shown you, right? During the invention, this is how they have created the point contact transistor. So that's how they came up with the symbol. And how do you give the direction? You see, this is N, this is P, this is N, okay? And this is your emitter, say this is base. Sorry, let's say this is your collector, this is base, this is emitter. So base emitter junction is forward biased, so P to N. So that is how your P to N diode symbol is there, right? And similarly for PNP, you can simply say that same funda. Here you use your emitter, base, collector. This is P and P. So this is your emitter base junction. Okay, your diode is like that. So from this way you can remember the symbols, right? So if we just do this, and if we solve this, this should be, this to be forward bias, it has to be 0.7 volt, right? So if I apply KVL in this loop, then 2 volt minus IB into RB minus 0.7 volt minus I, the current flowing here is IE, current flowing here is IC, current flowing here is IB, minus IE into RE equal to 0. What are known? 2 minus IB is known, right? How IB is known? IC, they want us to, collector current, IC, they want us to find 2.8 milliampere. Divide by your beta, right? We have seen, right? This IB will be IC by beta in forward active mode. So this minus your 0.7 volt minus IE, we can simply write IE equal to IC because beta is 120. So 120 plus 1, 121 and 120, we can take it similar. So IE we can write 1, it is 0.8 only, 0.8 into 0.68, right? This is milli, this is kilo. So your 1.3 and there is one RB. 1.3 minus your 0.8 into 0.68 is 0.544 is equal to 0.8 by 120 into RB, right? So your RB is coming out to be, sorry, 120 divided by 0.8. 113.4 kilo ohm, right? So your correct answer would be this D. In this way you can analyze these circuits very easily. So let's move on to the next problem. RB is set to the value obtained. RB is, we got 113, right? 113 kilo ohm. So, and for this RB, we have seen that IC is 0.8 milliampere, right? Now they wanted us to find out this. See, this is your VCE, right? This is your C, this is B, this is E, and this is an NPN transistor. So if I just apply KVL in this loop, you have 12 minus IC, this is your IC, this is your IE, this is your IB. Okay, so if you have IC RC drop minus VCE minus IE RE drop equal to 0. So 12 minus this is 6 equal to IC and IE we can take similar because my beta is much more than 1. So IC we know 0.8, so RC plus RE, right? So 6 by 0.8 equal to, what is my RC? I need to find out, right? RE is given as 0.68. So 6 divided by 0.8 minus 0.68. Minus 0.68. So it is coming out to be 6.82 kilo ohm. So this is your right option, right? A pretty simple problem. So now we want to find out what RC said to be value obtained at Q8, right? RC we find at 6.8 kilo ohm just now, 6.8 kilo ohm. What is the smallest value of RB for which will cause the BJT to enter saturation? BJT at saturation, see, let us go to this plot, right? Say this is after this, my IC is saturated to IC sat, saturation current, right? That means even if we increase my VCE, my output current or collector current remains saturated. At that point, at which point the value of IC gets saturated, we call it as VCE sat. This is the boundary, right? This is the boundary of your forward active and saturation region. Okay, so your which will BJT enter into saturation. So this I can safely take as 0.2 volt, right? If we take this at 0.2 volt, then I need to find out what is the smallest value of RB, right? So let us apply KCL here, KVL here, assuming that this is 0.7 volt because this had to be forward bias. Why? Because at saturation or at forward active, my base emitter junction is always forward bias. Remember, in saturation, in forward active, base emitter junction is always forward bias. That means my VBE for an NPN transistor, we can assume it to be 0.7 volt. Okay. So if we assume it to be 0.7 volt, then applying VI is nothing but KVL at base emitter loop. We have 2 minus IB into RB minus 0.7 minus IE into 0.68 is equal to 0, right? So 1.3 is equal to IB into RB plus this 0.68 into, what about this IE? IE is nothing but equal to IC beta IB, or even if you do not take it, it comes at beta plus 1 IB, right? Even if you let us do this problem to be precise, or we can just simply take 120, nothing, it doesn't matter actually. IB into, that's all, 0.68 we have taken earlier. So your IB remains 1.3 divide RB. RB is unknown, right? RB we need to find out. Now 0.68 into 120 becomes 81.6. Okay. So here we find out IB. Now let us go to outer loop for KVL at outer loop. That means this one. 12 minus IC RC. RC is what? 6.8, right? Into 6.8 minus VCE is 0.2 minus IE is almost IC into 0.68 equal to 0, right? So this becomes my 11.8 equal to 6.8 plus 0.68, 7.48, right? 7.48 into IC. IC is beta into IB. That means 11.8 equal to 7.48 into 120 into 1.3 by RB plus 81.6. So your RB plus 81.6 is equal to 1.3, 120, 7.48 by 11.8. Okay, let us calculate. So RB is coming out to be 98.88 minus 81.6 minus 81.6. It is coming out to be 17.2 kilo ohm, right? We have any option? Okay, so the nearest one is this 16.7, right? As it is an approximate analysis, you can simply guess the nearest value, right? So your answer C is correct. So let's move on to next problem, problem number 10. Okay, first thing what I noticed that it is a PNP transistor, right? Remember the arrow is given at the emitter base junction. Okay, even if I draw it like this is my emitter, this is my base, this is my collector. This is P, this is N, because the diode is directed from P to N, and then obviously this will be P, right? Similarly, if I take this case, this is my emitter, this is my base. First thing, don't do this. First thing you do that this is P, this is N, this is P. Get first cleared that it is a PNP transistor. Then you check Where is my emitter base junction? The junction with arrow is the emitter base junction. Now I need to find out whether this is base or this is emitter. You can simply see this is C, this is emitter, this is base, and this is collector, because you know the base is like the horizontal, this vertical line, right? So see, these are very basic stuff. I'm repeating this again and again because the new students, just first year or second year undergrad students, make this mistake, right? So we see that it is a P transistor, then current, so like acts like a current source, making a constant current flowing through the load resistor. What is the load resistor here? It is nothing but your collector resistor, right? And your IL is nothing but here IC, that means collector current, and this is collector current. What does it mean by a constant collector current? How do you know that which mode it is operating? Now let us revisit the thing of this output characteristics, right? You see in this output characteristics, the constant collector current, that means this, right? What do you mean by current source? Irrespective of the load, that means the potential drop across it, the, the current should be constant, right? How does a ideal current source characteristics look like? If I ask you, let me go to that page. If I ask you current source, right? Current source mean I constant. That means your IV will look like, suppose this is your current source, this is your V, this is your I. So your characteristics will look like this, right? This is I, this is V. That means in IV characteristics, if you find a straight line or a horizontal line parallel to the voltage axis, that means that there is a current source phenomena going on, or the current is constant for certain region where the line is straight, right? So in this case, if you now see this IC versus VCE, if you find the characteristics is like this, you see that in this region, the current is constant, a collector current is constant. That means, what is this region, by the way? This region is nothing but your forward active region, right? So from this point, making it as a constant current source, irrespective of the value of RL, that means you are sure that it is operating in a forward active mode. Okay. Now see, as long as RL less than RL max, if the diode voltage drop is taken to be 0.7 volt, that means net drop is 2.1 volt. That means this node voltage is 15 minus 2.1 is how much? 12.9 volt, right? If it is 12.9 volt, if it is 12.9 volt, this has to be in forward active, right? Forward active means emitter by base junction, forward bias. That means VEB is 0.7 volt. This is your 0.7 volt, right? So if this is your 12.9 volt, this is drop is 0.7 volt. So can I say that this voltage is 13.6 volt? Just this plus this is simple KVL only, right? 13.6 volt. Now they have told us that IL is 1 milliampere, right? What was the question? The question is the diode voltage drop is taken to be this. What is the value of RE required to obtain a 1 milliampere, right? Here beta is not given. That means I can assume beta to be very large. That means I can assume my collector current beta very large. I can assume my collector current to be equal to my IE. Collector current is nothing but IL. So IE is nothing but IL, 1 milliampere. So this current is 1 milliampere. This potential we know, this potential we know. Can we find out RE? Yes, we can. So my RE will be 15 minus 13.6 divided by 1 kilo ohm. 1 is nothing but milliampere here. So this is nothing but 1.4 kilo ohm, right? So is there any option? Yeah. B is your right option. In this way, you can find out this voltage. First, you need to make sure that which region you are operating at, right? So next, in the circuit of Q10, okay, what are the values? What are the things we know from Q10? From Q10, we know that this is 1.4 K, right? This is zero point 0.7 volt. We need to find out RL. So RL will be RL max when my device is at forward active saturation boundary. How do I know that? Read the last question. The circuit shown in the figure behaves like a current source, making a constant current flow through the load resistor RL, irrespective of the value of RL, as long as RL is less than RL max. That means this condition, this forward active region condition, this is valid, or the current source behavior will be valid as long as my RL is less than RL max, right? So my RL max will be at this boundary. That means my forward active and saturation boundary. From that, what we can deduct that my this voltage will be zero point 0.2 volt, right? Do you agree? So if you agree on this, then just wait a minute. I think this is the right convention, right? Because it VEC now is positive for PNP transistor. Remember that. So your 15 minus KVL at the outer loop. 15 minus IE RE minus 0.2 minus IERL equal to 0. 15 minus IE was 1 milliampere earlier. So 1 milliampere, sorry, IL and IE are same. So you have 1 milliampere and 1.4. So this becomes 1.4 minus 0.2 equal to 1 milliampere into RL. So this becomes 14.8 minus 1.4 equal to 1 milliampere into RL. So your RL becomes 13.4 kilo ohm, right? So A is your right option. Okay. So let's move on to next problem. What is the diode current in the circuit? Okay. This is very simple, I think, because we have been assuming beta to be very large. What is going on? We were assuming IC equal to IB, beta very large. That means IB is almost equal to 0 ampere. Okay, so if this is my base current and this is 0 ampere, so current flowing through this is nothing but current flowing through this from KCL, simple KCL, right? So what was the potential at this point? 12.9 volt, right? So what is this current? Let's say this is I2, let's say this is I1. So your I1 will be nothing but I2. What is I2? 12.9 divided by 4.7 milliampere. That is your 2.74 milliampere. Okay, so this is your right option. So what we are dealing now is that simple biasing of BJT circuits. Next week we will see some more sophisticated usage of this BJT circuits. Some amplifiers we will see. Maybe if time permits, we will see some switches also. How BJTs are used as switch. But this is simple biasing scheme. Even it is not all the biasing schemes, right? There you can have feedback by various kinds of feedback mechanism will be going on because these circuits are very sensitive to your some device temperature, right? Say device temperature, it is very sensitive because these all are semiconductors. If your device temperature changes, your mobility changes, your resistivity changes, and entire property of your semiconductor is altered, right? Not altered, it changes. If it changes, then we have to be very careful that, see, even if you are making a circuit with some semiconductors in it, right? You want it to use, suppose you are using your mobile phone in some, let's say, in some Himalayan region, right? There is cold, there will be some kind of mobility for the devices, and there for that temperature the semiconductors in your device will have some kind of mobility. And suppose you are in Chennai where the temperature is little bit higher, so there you have a different temperature. So do you want your mobile phone to go behave bizarrely in two places? To do not, right? So you need to find out some circuit techniques which can take care of this kind of changes. These kind of changes are taken care by negative feedbacks, right? So this, I think you will go through the lectures and various kind of biases like voltage divider biases and other kind. This is basically the fixed bias. So far we are discussing. So various kind of biasing you have, we will be taking, you will consider the Q point position, the quiescent point. Okay, we will go through the lectures and then we will discuss some problems on that. So let's move on to the next thing. In the circuit shown in the figure, assume that the BJT has a large beta. Okay, large beta means we have been seeing beta large means your IC is equal to IE. What value of VB is required to obtain IC equal to 1.2 milliampere? Okay, IC is 1.2 milliampere, right? This is your zero point 0.7 volt. So if your VB minus 0.7 minus IE into 0.68, because this is 0.68 kilo ohm, plus 5. It is not grounded. See, note that it is some negative potential is there. It is generally the preferred way to bias a circuit. Instead of a 112 volts, one, let's say 10 volt supply at the collector, you can distribute it to 5 volt at the collector and minus 5 volt at the emitter, right? There are some distinct advantage for doing this. This we'll discuss later if time permits. So you need to find out the value of VB, right? For IC equal to 1.2 milliampere. So this is, I think, pretty simple. Plus 0.7 plus 1.2 into 0.68. One thing you should be very focused about, that keeping track of the current and resistance units, right? I am using throughout the lecture kilo ohm and milliampere. So it will, whenever it is multiplied, the voltage unit is always volts, right? Plus 0.7 minus 5. So it is coming out to be VB equal to minus 3.484 volt. So do we have any option? Yeah, this is the right answer. Okay. Similarly, moving on to the next problem. Okay, it is quite similar, right? So we can just simply use the formula from above. VB is nothing but minus 5 plus 0.7 plus, instead of 1.2 milliampere, they have mentioned it 5 milliampere. So we have 5.68 plus 0.7 minus 5, that is minus 0.9 volt. This is the right answer. See, this case, one thing you need to be very careful about, that the operating regime, right? You know all the values, you check how to ensure it is in active region, right? Or forward active region. Forward active region. You check your VBE, you have assumed to be 0.7 volt, right? You check your VCB, right? For that, you find out VCE from outer loop, and you know VCB equals to nothing but VCE minus VBE, right? This you can find out this. So this need to be reversed biased. Ensure that. For an PNP transistor, this is an NPN transistor. NPN transistor, your collector is NPN. Collector is N, right? So your VCB should be positive. Remember that. This also I have shown earlier, right? This is VC. Okay, this is PNP. So for NPN, this has to be this, right? So this is your C, this is B. So your VCB should be positive. Okay. So this is fine. So you ensure that the region, right? Region of operation is correct. This will be a validation check at the end of each problem you do. The next one is, last one is the maximum value of VB for which BJT operates in the active mode. Maximum value of BJT operates in the active mode. That means you need to consider this as your 0.2 volt or the boundary VC is at. Here you find out 5 minus IC into 0.82 minus 0.2 minus IC, because IE and IC are same, into 0.68 plus 5 equal to 0. That means 10 minus 0.2, this is this taken minus 0.2. That means your 0.82 plus 0.68 is your 1.5 into IC. That means your IC is equal to 9.8, 0.5 is equal to 6.53 milliampere. Okay, then what is the value of VB required? VB minus 0.7 volt minus IE is equal to IC here. So IE or IC into 0.68 equal to 0. So your VB is nothing but 0.7 plus my 1 plus 5 volt is there, right? Plus your 6.53 into 0.68 minus 5. So minus 4.3 plus 6.53 into 0.68. It becomes your 0.1404 volt. So this is your right answer. Okay. Okay. So we end here today. So do practice this problem very diligently, right? And we still have 3 minutes. If you have any question, you can simply unmute and ask. I will wait for 3 more minutes. Next week we'll be meeting with BJT problems again, but it will be more on the circuit specific. Today we have discussed basics of biasing and some how the emitter based junction and collector based junction operate basically, right? Yes, Gauri,
Hello, sir.
please.
Hello.
Yes, please go on, Gauri.
Sir, point 2 volt value assume.
Oh, see, this is let me show you. There was an instruction given. This was the instruction, right? Assume that NPN, this active operation, this is for all the problems. VC is at,
Okay, sir.
right? So you see, when you are at this region, right? When you are at this point is nothing but your junction of saturation and forward active region, right?
Okay.
So at this point your VC set remains 0.2 volt. Make you note that even if it is not given in any problem, right? You can safely assume it between zero point 0.1 to zero point 0.2 volt. You can
Oh,
assume it. Okay.
okay, sir.
So you guys are crediting the course or auditing simply? Means you guys are enrolled for the course and doing for the certificate?
Yes, sir.
Okay, so you are submitting the assignments timely?
Yes, sir. First two assignment missing. Otherwise,
First, okay, first two assignments missing, right? Okay,
huh.
you can at least try, right?
Yes, sir.
So you are a student in first year?
Last year, sir.
Acha, final year. Okay, you are from electrical branch, right?
Yes, sir.
Okay, okay, fine. Okay, you guys do the problems diligently, and that will help you actually in your
Okay, sir.
placements and also, right? If you have any question, you can comment in the this channel in the YouTube video, which we will be sharing all the TS, or you can simply ask in the discussion forum, which is more preferred for us, which is in the Swayam portal, right? There is one
Yes.
tab, ask a question. You can always ask there referring to the video and the timestamp that this point I do not understand. Someone will reply. Okay?
Okay, sir.
Okay. So fine. So thank you everyone. Let's end the discussion here.